Let me tell you a joke. Somebody apparently once went up to the great philosopher Wittgenstein and said what a lot of morons people back in the Middle Ages must have been to have looked every morning at what's going on behind me now, the dawn, and to have thought that what they were seeing was the sun going round the earth. Well, as every school kid knows, the earth goes round the sun, and it doesn't take too many brains to understand that. To which Wittgenstein replied, yeah, but I wonder what it would have looked like if the sun had been going round the earth. Point being, of course, it would have looked exactly the same. You see what your knowledge tells you you're seeing. Because the astronomer priest here, who had a go at clearing up the confusion in the sky, succeeded, and in doing so blew everything to kingdom come, if you'll forgive the phrase. Let me explain why his work was so revolutionary. See, back at the beginning of the 16th century, what was up there was what Aristotle said there was, had said 2,000 years before. It was a straight common sense, as I see it, view. Let me show you a model of it. Here, at the center of everything, the Earth, static. Well, you can't feel any motion, can you? All around here, on concentric crystal spheres, pushed through the sky by angels, the moon, the sun, the planets and the stars. All wheeling around once a day in heavenly, unchanging circles. Well, they do, don't they? Heavenly motion was evidently circular. Here on Earth, on the other hand, things only moved one way, in straight lines, up or down. So, if celestial circles were eternal, obviously, straight-line earthly movement had to be the reason we weren't eternal. Movement special to Earth. Okay, this priest here, in 1512 or so, took a closer look at the heavenly arrangement and didn't much like what he saw, which was Mars, for instance, among others, being very un-Aristotle. I mean, it appeared sometimes to go backwards. Now, that was supposed to be impossible. So people had got round the difficulty with this little gizmo here. See, there's Mars. It goes forward on its main circle, while on an extra mini-circle it goes backwards. Backwards. Good, eh? Solved the problem. Trouble was, to make the entire solar system work in pure Aristotle terms like that, took over 90 of those little fiddly bits. It occurred to Copernicus, our priest, that there might be a simpler way that would still be circular and that would allow for things seeming to go backwards. So he came up with this. If you put the sun at the center and the Earth in orbit, then you know what we now know, that view of Mars going backwards isn't real. It's because it's in a slower orbit further out than Earth. Most of the time, everybody appears to be going forwards, and then when we pass Mars, it appears to go backwards. And then at other times, forwards again. And similar problems for the whole sky were solved by this sun-centered system. Copernicus published his manuscript in 1543, just in time for the Council of Trent. So, you're a church father. What this new system of Copernicus is saying is this. The Earth moves, although the Bible says it doesn't. It's no longer at the center of God's universe, although the Bible says it is. It's a planet, so heaven and earth are no longer separate. And Aristotle is wrong, though church authority depends on Aristotle being right. So, you're a church father. You pick up this subversive, heretical, revolutionary lunacy, and what do? Foam at the mouth, right? Wrong. When the Council of Trent got round to reading what Copernicus had said, they were delighted. His new system would make calendar reform more precise. And the business of turning every basic belief regarding the nature of the universe upside down? A mere bagatelle. Since from the Church's point of view, back here in Frombork, Copernicus was talking nonsense. Literally. After all, astronomy drew lines and circles up there in the sky, but they weren't really there, were they? They were a mathematical convenience for measuring or teaching astronomy. While the Copernican system might well have been brilliant mathematics, nobody thought for a second he really meant the Earth was whizzing around the sun. Don't be silly. That kind of talk would blow holes in everything. Most unfortunately, it was already too late for that kind of talk. Nothing immediately theologically dangerous, you understand, just some people asking questions about what Aristotle had said about motion on Earth. What were they up to? Nothing much. Just blowing holes in everything. Well, guess what happened next? Yes, only this time the mathematics professor involved slowed the falling ball process down by rolling his balls down a slope, marked with numbers at equal intervals to see how long it all took. He used a pendulum swing to get split-second timing on when he released each ball. He spent months rolling different weight balls down different angle slopes, hundreds of times, so as to get accurate average figures, and each time watching how long it took the ball to go different lengths of the slope, a third, quarter, fifth, eighth, half, and so on. He measured the time with water. As the ball rolled whatever distance it was supposed to, he'd run water at a steady rate into a measuring jar because he could see immediately from each amount whether the ball was taking different times to do different bits of the journey. In other words, if it was accelerating as it went down the slope. What Galileo was looking for was some kind of law that all falling objects obeyed. In 1604, he found it. Everything accelerated as it fell at exactly the same rate, by Galileo's law we all learnt at school, 32 feet per second per second. It was the first time nature had been described by mathematics that could be used in any circumstance to describe what nature was doing, the beginning of what we know today as the scientific revolution. Now, all that may look very mathematical and esoteric to you, but in 1605, doing that kind of thing with balls was dangerous, because what Galileo had discovered was the thing that Aristotle said couldn't exist, a universal law of acceleration that every single falling object on Earth would obey, and never mind all that nonsense about each object its own unique characteristic. Now, contradicting Aristotle like that could have made life very hairy for Galileo, had events not taken a turn for the safer, with a new business proposition. In July 1609, a friend of his showed him the new wonder machine from Holland, a telescope. And 1 month later, Galileo was here in St. Mark's Square at Venice with a financially very attractive idea in long-range optics. Up here, he said, look through this, he suggested to a group of shipping merchants. Galileo's new improved version of the optical gizmo would magnify distant objects 9 times, and that meant that you could spot the ships coming into anchor out there, a full 2 hours ahead of the average naked eye. And that meant that you could get out your little commodity list, ship symbol, cargo, value, and fix the market prices accordingly, because you knew the ship was coming in and your customers didn't. Nice idea, they said. We'll take 30, and here's a fat salary to keep it in the family. But a bull-headed, arrogant exhibitionist like Galileo couldn't keep his mouth or his options closed. And in 1610, he did something only a lunatic would do. He pointed an even better version of his telescope at the one place Aristotle and the Church said not to. Up there. And when he saw what he saw, he compounded the felony by going public in a little 24-page booklet called The Starry Messenger that blew 2,500 years of authority and status quo right out of the window. Because in a few scribbled illustrations, Galileo took the universe apart. Look, here's the moon. Not perfect and incorruptible like Aristotle said it was, but with mountains, just like the Earth. And millions more stars than there were supposed to be. And look at this, the unthinkable. 3 or 4 little satellites going round Jupiter when everything was supposed to go round the Earth. And a bit later, here he is saying that even the sun isn't perfect. It's got spots. And then the clincher, Venus looked like the moon sometimes, waxing and waning. And that meant that we were seeing it illuminated differently as it went round the sun. So all of this was visible proof that Copernicus was right after all. Everything went round the sun. Even then, Galileo might have managed to keep things sweet, had it not been for one breakfast time when his boss's wife, the Duchess of Tuscany, asked a friend of his if all this didn't mean that when the Bible said the earth stood still, it was wrong. Well, in a polite letter explaining things to her, Galileo said yes, and not to put too fine a point on it, scientifically speaking, the Bible was wrong. And then everything hit the fan. Now, the conventional view of what happened next is that the Church decided to arrest Galileo and shut his mouth for good. Well, he was arrested and shut up, but only after an infuriated Church had bent over backwards not to. They said, look, we know you're right, but you can't just spring it on the masses. You've got to let us tell them slowly. Galileo told them to get lost. Then he was arrested. Copernicus was prohibited, and that, for the Catholic Church, was that. Well, fortunately, Galileo hadn't blown it for everybody. Not up here in Austria, in the Protestant town of Eferding. And why are we here? Well, you recall Brahe. He'd finally gone off to work in Prague, still worried about those wobbling orbits. You remember the comet he saw coming into the solar system on an oval orbit and couldn't figure out how an oval path would remain stable without rolling around. Like an oval wine barrel did when you put it down. Well, it was wine barrels that provided the answer, the same shaped barrels they're delivering here now, brought to this castle back then in 1613 for a wedding. The groom was a local maths teacher, a fellow called Johann Kepler, and his blushing bride, the adopted daughter of the people who lived in this castle. Now, Kepler had just come back from Prague, where he had been Brahe's assistant, and being a short-sighted fellow had tended to concentrate on the paperwork and the calculations, rather than actually staring up at the sky. So when he saw the local Eferding delivery men checking the wine in his barrels in what he took to be a rather imprecise manner, I mean, same dipstick, but different shaped barrels, he decided to take a look at wine barrel mathematics, a piece of cake when you had cut your teeth on measuring planetary orbits, which is what he'd been doing night and day for 11 years, trying to make sense out of what Brahe had left behind when he died, a gigantic pile of nocturnal note-takings. Apart from convincing Kepler that the planets did go round the sun, Brahe's mountain of data revealed something that shocked Kepler rigid. Mars was circling the sun, but it was speeding up and slowing down as it went. And when he checked the figures to see if he'd made a horrendous mistake, he realized that all the planets were going at different speeds. The further out from the sun, the slower. But why? The only explanation for the figures was a kind of magnetic force from the sun, strong near it and weaker further out, a force pulling the planets into orbital paths like Benedetti's swinging stones, or into lopsided orbits that sped up close in and slowed down further out, and stayed that way because the force was always there to keep the planets repeating exactly the same path. But was he right? It took Kepler 4 years to work it out. Mars wasn't changing speed at a regular rate in a circle, and nor were the other planets. It was doing it in an ellipse, and it was doing it like clockwork, the change in speed exactly relative to the distance from the sun. Close in, going fast, taking a month from there to there. Far out, going slow, a month from here to here. But these areas, exactly equal. You'll notice that I'm drawing little triangles like Kepler was. That's because that's how they measured orbits. You split the orbit into zillions of little triangles and used them to tell you the area and the approximate length of the orbit. And that's why Kepler's new method for measuring wine barrels, which incidentally proved the dipstick method was fine, was such a big deal for astronomy. It was immensely accurate. Look, Kepler split each barrel into zillions of little cross-sections like that, each one of which, on the edge, would look something like this. Now, a rectangle is easy to measure, and you fill this one almost with a little triangle. That little leftover bit there is minimal. That's why I keep using the technical term zillions. The more sections you make, the smaller those little leftover bits there become. And if you have an infinite number of sections, you get no leftover bits at all, and total accuracy on the curve of a barrel or the curve of an orbit. Which was all amazing stuff and advanced the state of the art of orbital dynamics, as it's called. But it did create a problem almost as big as the one it solved. Kepler might have been a genius at getting the sky to work according to his sums, which left only the mind-boggling problem of working the sums out. Every time you wanted to check something, you were back to that ridiculous business of horsing around with zillions of little triangles. There had to be a better way than this. Well, when it came to sums, here was the place. Holland, the home of sums, commercial sums. And flat, sober and cosmopolitan, the Dutch loved science, if it made money. That's really all Amsterdam got worked up about. Financial matters, cash flow, bridging loans. Incredibly, they didn't care about what the rest of Europe was burning and torturing people for. The dull middle-class Dutch let you say and do and think almost anything you liked. The first truly tolerant nation in Europe, and because of it, knee-deep in refugees. One of which, a French thinker called René Descartes, in 1637, came up with an entirely new way of looking at everything, including, of course, balls in the sky. Look, however I move, I'm either going along or up, aren't I? Descartes tried setting that movement against two scales, one showing how far up, the other how far along. So, run me by again with numbers. Up 1, along 5. Up 2, along 16. Up 3, along 25. And you could describe any movement like that on Descartes' new graph. Now, suppose I want to do that with a cannonball. Say I want to shoot it out at 100 feet per second, like this. Here's the trajectory. Here's the scales. Call up y and along x. So you can describe this trajectory in x's and y's. And you could put in Galileo's law, Tartaglia's air resistance, speed, anything, and fire your cannon on paper, because now you could fire it in an equation. Now you see what that means. With a system like that, there's no more mumbo-jumbo. Just mathematics that you can now use to describe and predict everything. Even the stuff you can't handle, like the planets. you needed to get the really precise data you could now handle with your fancy new maths was instruments. And there were none better than those made in mid-17th century England. Calculators, logarithms, slide rules, vacuum pumps, microscopes, theodolites, quadrants, thermometers, barometers, clocks. The new instruments and techniques made it possible to examine everything from the microscopically small to, more important for us, the astronomically large, and start getting really accurate figures. The fellow who put it all together, literally, why Benedetti's stones went off in a straight line when you let them go, why Galileo's balls fell at the same rate, why Kepler's planets went fast in round the sun and slow far out from it, and the clever way that Descartes could turn trajectories into algebra, the fellow who put all that together was the first person in history who could have explained mathematically what I'm about to go through now, and why the whole universe goes through it. What am I talking about? This. Galileo's accelerating fall, now. Benedetti's outward swing, now. Kepler's orbits with their changing speeds. And then slow down as I go over the top. Fortunately for the fellow who made sense of it all, he didn't have to go through this. He says he just sat and watched this. He reckoned the force that made things fall was the same downward pull as the one Kepler said held the planets as they swung around the sun and stopped them flying off like Benedetti's stones, because this force attracted everything to everything else. He worked out a formula for how the force should operate based on how far apart things were. Well, he knew the moon was 60 times further out from the center of the Earth than he was, so he tried his formula on the moon. The pull of the Earth ought to be acting like a hold on the moon, counteracting its tendency to fly straight off into space by exactly the amount of force required to keep it in orbit at that distance. So our genius, using an advanced form of infinitesimal calculation, you remember Kepler and the wine barrels, worked out where the moon's path ought to go if the force acted, as his formula said it should, that far from Earth, at 44 thousandths of a foot per second, bending the moon's path inwards. Sure enough, that's just what the moon did, to the inch. His formula explained what everything else did too. Planets, pendulums, apples, fairground swings, everything. The force Newton named gravity kept the universe balanced, made it work, and brought heaven and earth together in one great equation. And just as his formula would tell you when what went up would come down, so it told his friend Edmund Halley when the great comet he saw leaving the solar system in 1680 would come back, exactly 77 years later. We end the story where we began, here in the Empress Maria Theresa's palace in Vienna. Because the year Halley's comet was due back, 1757, there was a fellow here who was, so to speak, to dot the I's and cross the T's on the whole affair. He was a Jesuit astronomer and mathematician, engineer, geographer, geodeticist, and general genius called Roger Boscovich. Now, Boscovich had done a lot of work on comets, like how to get a very accurate handle on their trajectory from any 3 observations. And he'd put in a prize-winning paper to the French Academy of Sciences, he was one of their foreign correspondents, on the interaction between Jupiter and Saturn. And it was through that enormous gravitational tug-of-war that the returning Halley comet had to come on its way back into the solar system. The question was, when? That's why the Boscovich work was kind of vital to the French astronomers watching for Halley, because it told them that the comet would be returning late, even before they picked it up on their telescopes. Thanks to Boscovich, they knew it would be 19 months late. I said Boscovich ended the story for another reason too. He was, among his many talents, like fixing the cracks in Maria Theresa's library, also science advisor to the Pope. And it was mainly due to him that the prohibition on Copernicus would be lifted. Fittingly, the great work went back into general circulation on the library shelves of Europe in 1758, the same year Halley's comet finally came back. Ultimate physical proof that Newton had been right, that the universe was ruled by mathematics. Well, that was the end of friend Aristotle, and magic crystal spheres in the sky, and questions science shouldn't ask, and the beginning of our modern world dominated by science and technology, and the confidence they give us to explore everything from subatomic particles to the ends of outer space without fear. Mind you, you need the confidence. If, as Kepler said, and Newton proved, it all does work like clockwork, there is nobody out there to care. Well, it may be fun to explore nature, to boldly go where no man has gone before. But in Newton's universe, you're no longer the center of attention while you do it. You're on your own, just a cog in the cosmic clock.